Dear colleagues, our research team present a study titled Application of Artificial Neural Networks for Prediction Energy Consumption of a Mining Enterprise. The authors are Victor Butcher, Valery Tituk, Valery Kuznetsov, Vitaly Kuznetsov, Andrei Romanets, Yuri Shertnov, and Petro Hupsky. Presenter is Vitaly Kuznetsov. The issue of forecasting electricity consumption remains a challenge, especially for industrial facilities with high energy intensity and uneven load patterns, such as those in the mining and processing industry. Traditional methods for estimation energy use often fail to account for dynamic changes in load structure, including seasonal, technological, or operational factors. Inefficient management of active and reactive power can lead to reverse effects such as grid overloads, increased transmission losses, and poorer power quality, all of which can negatively affect equipment stability and performance. The need to accurate forecasting of active and reactive power consumption stems from the growing importance of effective energy management in modern enterprises. With energy carrier prices steadily rising, optimizing electricity consumption is crucial to keep enterprises competitive. Additionally, forecasting reactive power is key to ensuring the stability of energy systems. Judging of overlooking reactive power requirements can reduce equipment efficiency, increase maintenance costs, and shorten equipment lifespan. Um, Precise forecasts helps determine the need for compensation devices and improve their efficiency. Therefore, enhancing the accuracy of active and reactive power consumption forecasts not only reduce operational cost but also improve the reliability and stability of energy systems, making this research highly relevant. On this slide, you can see the experimental data. The experimental data consists of the information about active and reactive power consumption for the workshops substation and the main step-down substation of a mining and processing plant in the city of Kryvyi Rih in Ukraine, collected over a 1 month period. The data was recorded at the 30-minute intervals. In our study, the initial data consists of an array with dimension 1440. Graphs of the initial experimental data from one of the sources are shown in figure 1. The time of the abscissa axis of the figure here and below is indicated in samples every 30 minutes, the number and the sample number. The next slide, forecasting result using statistical methods. To explore a statistical forecasting method for time series, we used implementation of key algorithm in MATLAB. The 18 results are shown in figure number 2 and figure number 3. On this slide, forecasting result using nonlinear autoregressive artificial neural network. For energy consumption forecasting, we used artificial neural network with nonlinear autoregressive architecture in various configurations, which is widely applied for time series prediction. In our study, we will denote a nonlinear autoregressive network with n hidden layer neurons and d previous value used as nonlinear autoregressive n and d. The artificial neural network's training process involves selection and learning algorithm and splitting the initial data into three sets: training data, test data, and validation data. In our paper, the data were divided as follows: 80%, 10%, and 10%. The data processing showed that relatively simple non-linear autoregressive networks can yield good results. By increasing the number of hidden layer neurons and the lag, it is possible to find artificial neural networks that perfectly reproduce the input signals from the training series. However, the data processing of testing and validation can lead to inaccurate results. Figure 4 shows the training results for various nonlinear autoregressive configuration using a series 1300 data points, followed by testing with a series 1440 points. Non-linear autoregressive artificial neural network with a small number of neurons are in sufficient lag tend to have significant absolute errors, while network with an excessive number of neurons and excessive lag generate unreliable fluctuations. The best result in processing the exciting data were achieved with nonlinear autoregressive 10.3 through nonlinear autoregressive 15.8. The next slide, improving forecast accuracy with data pre-processing. We hypothesized that the source of error lies in the noise present in the initial data caused by level quantization in the measurement equipment. For example, sigma equals 72 kilowatts, which inevitably introduce instrumental error E, while in practice it is E actual. This leads use to consider applying initial data pre-filtration. The results of filtering the initial data after a simple unbiased moving average was used are shown in figure number 5. Filtering this average over the arbitrary interval is accompanied by the smooth offload spikes, which significantly distorts the daily energy consumption pattern with apparent morning peak and energy usage. The next slide, smoothing with the filter of instrumental error. Fine. To improve the accuracy of energy consumption forecasting, an initial data filter called FINE, filter of instrumental error, was developed and tested. This filter removes noise within the threshold value without distorting rapid changes in the signal on the final energy consumption. The main idea is that in order to obtain the equivalent consumption value before and after filtration, the stored value are adjusted with discrete derivatives, active power and reactive power, so that the total energy consumption remains the same over a given interval before and after the adjustment. On this slide, you can see the figure number 7. This figure presents diagrams of initial data and the result after filtering with the proposed algorithm. Thus, small fluctuation in the initial data are significantly smoothed in areas with relatively slow changes, while faster spikes in energy consumption remain unchanged. The rule is determine the total monthly energy consumption for the filter signal does not exceed 0.2 or 0.5%. Using the proposed algorithm to pre-filter the energy consumption signal improves the accuracy of the forecast, as confirmed by calculation results. The root mean square error is reduced by 1.2 to 2.5, both in training and forecasting. And the conclusion. The study the mined experimental energy consumption data from three different sections of a large iron ore facility. In each case, time series to active and reactive power consumption were analyzed over 1 month period. Each of these series contains 1,414 data points. We suggested using the artificial neural network with nonlinear autoregressive architecture to energy consumption forecasting. It demonstrated the possibility in principle of applying such as artificial neural network to form short-term and medium-term forecast with satisfactory precision. To enhance the forecast accuracy, the study suggests conducting forecast based on the initial data pre-filtered with fine, the algorithm of which is outlined in our research. The calculation conducted indicates the availability of applying the proposed filter with a dead band of plus minus 0.05 maximum of power and filtering interval of 8 to 12 ticks, followed by training the nonlinear autoregressive type with configuration nonlinear autoregressive about 10.3 to non-autoregressive 15.8, where the ratio of training data, test data, and validation data is 80%, 10%, and 10% at in interval from 20 to 30 days. This allows for forecaster in the next 24 or 48 hours with errors of 2 to 4% for active power and up to 3 to 10% for reactive power, corresponding to 1 to 3 delta P. Overall, the nonlinear autoregressive model proved to be successful in forecasting. Thank you very much for your attention.